the quantum mechanics. So we are going to continue the quantum mechanics. Already two classes have been over, and today we are going to take the third class, in which we are going to discuss the conservation laws or theories of the conservation. See, the first law of conservation is the law of conservation of momentum, which is the linear momentum. When the total force acting on an object is zero, its linear momentum is conserved. Conserved means constant with the time. And the second law of conservation is the law of conservation of angular momentum. So when the total torque acting on an object is zero, its angular momentum is conserved. And the following is the proof for angular momentum. And you can see this is F vector into R vector. F is a force into distance. Force into distance. Force is rate of change of momentum. That is what we have mentioned here. P dot. Dot means anything differentiated with respect to time once. So P dot, that is dp by dt. So dp by dt is differentiating the momentum with respect to time once. Will give you the force, and the force into r vector. So that is the angular momentum. So d by dt of p into r, which you can see, first p is differentiated, r is taken as the constant, then r is differentiated, and p is kept as the constant. Normally the radius does not change. As the radius is not changing with the time, this particular part becomes zero. So d by dt of p dot r is equal to p dot r, which is equal to the torque. So p into r is angular momentum L, that is linear momentum, into distance is angular momentum. Then the rate of change of p into r is p dot r, which is equal to zero. Why it is zero? Because the total torque acting on the body is zero. When the torque acting on the body is zero, then P dot R is equal to zero. What is P dot R? It is differentiating PR with respect to time. Therefore, L dot is also zero, which means that L is a constant with the time. It is constant with the time. So when the total torque acting on a body is zero, then when the total torque acting on the body is zero, then angular momentum is conserved. Next, a law of conservation of energy. When motion takes place under conservative force, the total energy is conserved, which means that the total energy always remains constant. Look here, the proof for this conservation law is very important, and you have to understand this particular point. Suppose you are taking a body at the position 1 and it is shifted to the position 2. The work done in shifting the body from 1 to 2, W12 is equal to integral of 1 to 2 F into dr, where F is the force and dr is the, you know what is the integral distance. So integral 1 to 2, this is minus dV by dx. dV by dx is the rate of change, it is the differentiation of the potential energy with respect to distance. So force is a conservative force. So minus dV by dx into dx. So when you integrate this, you are getting it as minus V 1 to 2. So when you apply the limits, upper and the lower limits, you are getting V1 minus V2. Actually, this should be minus V2 minus V1. So I'm just changing V1 minus V2. Similarly, the work done. The force can also be expressed as P dot dr. See, when you think of the force in terms of potential energy, it is minus dV by dx. When you think of the potential energy in terms of kinetic energy, it is P dot, that is rate of change of momentum, is a force. So momentum is mv, mass into velocity is momentum. So integral 1 to 2 d by dt of mv dot dr, where m is the constant, so it can be integrated here, m into integral 1 to 2 v dv. So what you are getting, m v square by 2, 1 to 2. So it is half mv square 2, mv2 square minus half mv1 square. So this is kinetic energy T2 and this is kinetic energy T1. So that is equal to T2 minus T1. See, when you calculated the work done in terms of a potential energy, it was V1 minus V2. When you calculate in terms of kinetic energy, it is T2 minus T1. So from these equations 1 and 2, you can say V1 minus V2 is equal to T2 minus T1. So when you rearrange the things, you can say V1 plus T1 is equal to V2 plus T2, where this is the total energy in the first part and this is the total energy in the second position. So the total energy always remain constant. Hence the energy is conserved. Energy does not change with time. So these are the assumptions of classical mechanics. Now we come to the assumptions of classical mechanics. And the following assumptions, I request the students to be. So other assumptions of classical mechanics. The first assumption, there is no limit on the number of dynamical variables that can be determined accurately and simultaneously. The second assumption, there is no limit to the values that a dynamical variable can assume. Third assumption, there is no limit to the accuracy with which a dynamical variable can be determined accurately. And the fourth one, energy changes take place continuously. These are all the four important assumptions of a classical mechanics. I have already told you what is classical mechanics. It is the study of macroscopic bodies moving with velocity much less than that of light. So I have already told you what is a dynamical variable. There are a number of dynamical variables and we have seen them also. These dynamical variables, you can see here, I've just listed out various dynamical variables. So time is a dynamical variable, position coordinates or distances, they are also dynamical variables. Mass is a dynamical variable, velocity, linear momentum, angular momentum, acceleration, force, and then torque, and then work, energy, action, power. These are all dynamical variables. So there are a number of dynamical variables, and these variables, there is no limit on the number of dynamical variables that can be determined accurately and simultaneously. At the same time, you can measure any number of dynamical variables. So that is the first assumption. And the second assumption, there is no limit to the values that the dynamical variables can assume. It can assume any amount of value, any large number it can assume. And the third assumption, there is no limit to the accuracy with which a dynamical variable can be determined, which means that you can measure very accurately and simultaneously any number or any value of any dynamical variable. And also the energy changes take place in a continuous fashion. So these are all the four important assumptions of classical mechanics. Next, we are going to the equations of motion. The quantum mechanics involves many mathematical equations. Actually, I have already told you that mathematics is a language. Suppose if you want to convey any idea, that idea can be conveyed as completely as possible with a minimum number of letters using the mathematical language. So the motion, the movement, the dynamics of any body, a body which is moving in the motion. First, the motion was presented. It was written in the form of equation by Newton. Newton was the first person to observe that any body is moving under the working of conservative force. Look here, this is the very famous Newton equation of motion. F is equal to ma. Force is equal to mass times acceleration. But the main drawback of this equation is it is applicable only to Cartesian coordinate system. You may be knowing what is Cartesian coordinate system. I don't know how many of you know the Cartesian coordinate system and you remember. I think we have already discussed. This is Cartesian coordinate system, which is also called the rectangular coordinate system. In a rectangular coordinate system, a point on the space can be defined by three distances from the origin. Look here, this is the origin of a 0, 0, 0 point, and we are taking three mutually perpendicular axes, and any point on space can be defined, it can be described by three distances from the origin. This is Cartesian coordinate system. So this Newtonian equation, force is mass times acceleration, is applicable only to Cartesian coordinate system. But in other coordinate systems, it changes its form. That is the main drawback of the Newtonian equation. You look here, this equation can be written like this. Force is equal to mass times acceleration, which is equal to minus dv by dx, which is called the conservative force. It is the negative. It is the negative differential of the potential energy with the distance, which means that when distance comes down, the potential energy comes down. It is minus dv by dx. And T, the same force, can be written in terms of kinetic energy. T is equal to half mv square, which is equal to p square by 2m. Actually, mv square, I am introducing one m in the numerator and another m in the denominator. So it becomes n square v square, and in the denominator it is 2m. So when you differentiate partially with respect to velocity, dou t by dou v, dou t by dou v x, you are getting m into vx. So that is how it is differentiated, dou t by dou vx. That means dou by dou vx of half mv square. So what you will get, v by 2vx, m into 2vx divided by 2. So what you are getting is mvx. So d by dt of dou t by dou vx is m into vx dot, m into vx dot, which is equal to mx double dot. X is the displacement, double times differentiated with respect to time, which is equal to minus dv by dx, which is equal to force. Therefore, the entire equation can be written as d by dt of dou t by dou vx plus dv by dx. That is, this minus dv by dx is brought to the left hand side, so that becomes a plus dv by dx, which is equal to 0. So this entire equation is called the Newtonian equation of motion, which is a mathematical expression of the motion of a body under the influence of a conservative force. So it is a d by dt of dou t by dou vx plus dv by dx is equal to 0. So this is a Newtonian equation. Now look here, the next equation of motion is the Lagrangian equation of motion. This Lagrangian equation is superior to Newtonian equation because it retains its form in all coordinate systems. Lagrangian equation is not changing its form when you change the coordinate systems. It retains its system in all coordinate systems. That is the advantage of Lagrangian equation. This Lagrangian equation, you have to think of first the Lagrangian function L, which is derived from the principle of least action. It does not have directional property, but a Newtonian equation has directional property. But this Lagrangian function, actually we are deriving the Lagrangian function from the principle of least action. So this Lagrangian function is L is equal to T minus V, which is a non-directional entity. So what is L? It is half mv square, which is equal to half mx dot square. So dou L by dou x dot is mx dot. So when you differentiate this mx dot with respect to time, d by dt of dou L by dou x dot is equal to mx double dot, which is equal to the force, which is the negative gradient of the potential energy. So dou L by dou x is equal to minus dv by dx. So d by dt of dou L by dou x dot is equal to dou L by dou x. So I can write d by dt of dou L by dou x dot minus dou L by dou x is equal to 0. This is called Lagrangian equation in x-axis. But this equation can be generalized in all axes. D by dt of dou L by dou qi dot minus dou L by dou qi is equal to 0. This is Lagrangian equation. But Newtonian equation can be derived from Lagrangian equation also. Look at here. The Lagrangian function L is equal to T minus V, which is half mx dot square minus V. So dou L by dou x dot is equal to mx double dot. So d by dt of dou L by dou x dot is equal to mx double dot, which is dou L by dou x. So mx double dot is equal to minus dv by dx, which is equal to force, which is force is equal to mass times acceleration. So coordinate systems are equivalent due to symmetry of space. Symmetry of space leads to conservation laws, which means the rotational homogeneity. It gives the conservation of angular momentum, and the symmetry of the space gives the conservation of linear momentum, and the symmetry of time gives you the law of conservation of energy. So the symmetry and the homogeneity, so that is what is causing all these equations in the nature. Now we are going to discuss a very important thing, which is called the failure of classical mechanics. How the classical mechanics failed, how the quantum mechanics was successful in explaining very important concepts like a black body spectrum, the photoelectric effect, the heat capacity of gaseous substances, and also the hydrogen atom spectrum. So taking the black body radiation into consideration, black body is a device which can absorb and emit radiation of all possible wavelengths. There is no ideal black body in the universe, but a most perfect black body was constructed by Ferri, which is called Ferri's black body. And this is the structure of the Ferri's black body. See, it is an evacuated system. There is a small opening for the entry and the exit of radiation. The inner sphere of the Ferri's black body is coated with a lamp black material, and here is a small conical projection to avoid the loss of radiation by direct reflection. Suppose a radiation falls here, if this is a smooth surface, then the radiation can escape by direct reflection. If there is a conical structure here, the radiation that is falling here will experience multiple reflection, and it will be absorbed by the lamp black material. In the intensity of the radiation and the wavelength of the radiation on emission are plotted in a graph, and the plot is obtained in the following structure. So this was the structure of the plot. See, there is a particular lambda for which the intensity is maximum. This lambda, it goes on. See, when you change the lambda, lambda is minimum to lambda is maximum. And there is a particular lambda which is maximum in intensity. When people studied the black body spectrum, so the same thing was studied at various temperatures. At lower temperatures, the graph was like this. At a little bit higher temperature, the graph was like this. And a little bit higher and higher. And when you closely watch this, the peak, that wavelength comes with maximum intensity at lower temperature was here. When the temperature raised, the peak was shifted to lower wavelength region. And it is further raised, it goes to further left. And the temperature is further increased, it goes to further left. So which means that the black body radiation at different temperatures, the peak is moving to the lower wavelength region when the temperature is raised. This is called the Wein's displacement law. Actually, this graph has to be theoretically explained. We have to give a suitable explanation so that our explanation fits into the graph. Rayleigh-Jean's law, on the basis of equipartition principle, Rayleigh-Jeans formulated an equation to explain the black body radiation, which is rho lambda is equal to 8 pi by lambda power 4 kt. Actually, this kt is taken from the equipartition principle. So this is the total number of vibrators. When the total number of vibrators and each vibrator is contributing an amount of kt to the total energy of the system, so the rho lambda, the intensity of the radiation has to be like this. So according to this equation, rho lambda is inversely proportional to lambda power 4. So when you draw the graph according to this equation, you are getting a graph like this. So this equation holds good only in the higher wavelength region, but the original graph, it starts from here and goes to a peak and then comes down. But this graph holds good in the higher wavelength region. In the lower wavelength region, it is a failure. So Rayleigh-Jeans wanted to construct an equation within a classical assumption, equipartition principle, and the equation he got was successful only in the higher wavelength region, but it is a failure in the lower wavelength region. And Wayne constructed another equation with the same assumption. The Rayleigh-Jeans equation finds its application in the ultraviolet catastrophe. If you think of the Wayne's equation, he wrote rho lambda is equal to C1 by lambda power 5, 1 by e power C2 by lambda t. According to this equation, for the low values of lambda, C by lambda power 5 increases and 1 by e power C2 by lambda t decreases. For the higher values of lambda, C by lambda power 5 decreases and 1 by e power C2 by lambda t increases. So, but for the higher wavelength, the decrease is found more than the increase. Therefore, what happens? The equation, the graph drawn with this equation falls like this. So the Wayne's equation is holding good in the lower wavelength region. It is a failure in the upper higher wavelength region. Say Rayleigh-Jeans equation was successful in the higher wavelength region. Wayne's equation was successful in the lower wavelength region. Now we have to get one single equation which will behave as a Rayleigh-Jeans equation in the higher wavelength region and the Wayne's equation in the lower wavelength region. So that was the work done by Max Planck. So what Planck said? He said there are number of vibrators which are vibrating with different frequencies. And this is called the quantization principle. He quantized. The Wayne and Rayleigh-Jeans assumed it is a continuous vibration. All the vibrators are vibrating with equal frequency. And there is no distribution of number of vibrators and the energy of the vibrators. But Planck gave the quantum idea, he quantified, and the quantization principle, quantized energy levels were proposed by the Planck. And he said, In the first level with E0, N0, H nu N1, N2 number of vibrators are found with 2 H nu energy, N3 number of vibrators are found with 3 H nu energy, N4 number of vibrators are found with 4 H nu energy. Therefore, the total number of vibrators in the black body is N is equal to N0 plus N1 plus N2 plus N3. And also, he wanted to calculate the total energy. Total energy is N0 into 0, N1 into E1, N2 into E2, N3 into E3, and so on. And according to statistical methods, N1 is equal to N0 e to the power minus E1 by kT. So what is N2? N2 is N0 e to the power of minus E2 by kT. So total N can be written as N0 plus N0 e power minus E1 by kT plus N0 e power minus E2 by kT plus N0 e power minus E3 by kT. When you put x is equal to e power minus E1 by kT, N is equal to N0 plus N0x plus N0x square plus N0x cube and so on. So when you take the N0 as a common out, it becomes N0 1 plus x plus x square plus x cube and so on. So this series can be written as N0 1 minus x whole power minus 1. So the total number of vibrators N is equal to N0 by 1 minus x. So next, similarly E0, 0, that is the first energy is 0, plus E1, then N1, that N1 is written as N0 e power minus E1 by kT, E2 into N2, which is see E2 into N2, which is N0 e power minus E2 by kT. So again you substitute this quantity as x. It is E1 N0x, E2 N0x square, E3 N0x cube. So you can take N0 E1x out and you are getting 1 plus 2x plus 3x square plus 4x cube plus and so on. So this is equal to 1 minus x whole power minus 2. So the total energy is N0 E1x divided by 1 minus x whole square. So when you divide this 4 by 3, you can find out the average energy of the vibrator. So when you calculate the average energy, it is E1x by 1 minus x. So what is E1? What is x? E power minus E1 by kT. What is x? 1 minus E power minus E1 by kT. So for simplification, I multiply the numerator and the denominator by E power E1 by kT. I am getting E1 divided by E power E1 by kT minus 1. So when you substitute the value of the E as h nu, this is the equation that you are getting. That is lambda rho lambda is equal to 8 pi lambda power 4 hc by lambda divided by e power hc by lambda kt minus 1. So when the lambda is very large, what happens? E power hc by lambda kt becomes very less than 1. So 1 can be neglected. So the equation what you are getting is the Rayleigh-Jeans equation at the large lambda values. For the small lambda values, the same equation becomes Wien's equation. So the Planck's equation is an interpolation of Wien's and Rayleigh-Jeans equation. So this is how one single equation. So these are Planck's radiation law. For higher wavelengths, e power x can be assumed to be 1 plus x. So when you substitute 1 plus x, 1 plus xc by lambda kt, you are substituting in the equation, you are getting 8 pi by lambda power 5 into lambda kt. So this lambda will get cancelled. You are getting exactly the Rayleigh-Jeans equation. So Rayleigh-Jeans equation holds good in the higher wavelength region. And in the higher wavelength region, Planck's equation itself becomes a Rayleigh-Jeans equation. For the lower wavelength regions, e power hc by lambda kt is much greater than 1. Therefore, 1 can be neglected. So what you are getting, rho lambda is equal to 8 pi by lambda power 5 hc by e power hc by lambda kt. So put hc as constant 1, hc by kc2, what you are getting is rho lambda 8 pi by lambda power 5 C1 divided by e power minus C2 by lambda kt. This is Wien's equation. So one single equation which behaves as Wien's equation in the lower wavelength region and the Rayleigh-Jeans equation in the higher wavelength region. So this is the speciality of Max Planck's equation. Still plenty of things are to be shared about the Planck's equation. I think with this, the first 40 minutes is over. I request the students to rejoin.